Imagine a material that grows stronger over centuries, resists the ocean, and survives 2,000 years of earthquakes, weather, and decay. Modern engineers can't reproduce it, yet the Romans made it, and it still stands. From the Pantheon in Rome to the harbor piers of Baiae, Roman concrete is everywhere. Pantheon Dome, Rome, 43 meters wide, largest unreinforced concrete dome in history, still intact after nearly 2,000 years. Colosseum, Rome, massive amphitheater with exposed concrete arches that have survived millennia. Aqueducts across Europe and North Africa, channels that transported water for centuries without collapsing. Roman harbors, including Pozzuoli and Cosa, submerged in seawater for centuries, still holding their shape. Yet modern concrete, despite steel reinforcement, additives, and decades of research, cannot match this durability. This isn't legend. Roman concrete behaves differently at a chemical level, challenging what we know about material science. And it raises a profound question. Did the Romans know something we don't? Ancient sources like Vitruvius describe Roman concrete as a mix of lime, volcanic ash, water, stone aggregates. Simple, right? Modern engineers tried replicating it. They mixed lime and volcanic ash in identical proportions, added water, and even mimicked the original aggregate. But the results failed under the same environmental stresses that Roman concrete survived. Something else, some unknown variable in process or chemistry, made all the difference. Roman harbor concrete is particularly mysterious. Modern concrete in seawater. Cracks, steel reinforcement corrodes, structural integrity fails within decades. Roman harbor piers survive 2,000 years, show microcracks that self-heal, gain strength over time. Studies reveal that seawater triggers chemical reactions in the volcanic ash-lime mixture. Dissolved minerals form new crystalline structures. Crystals fill microcracks, healing the concrete naturally. This is a material that literally gets stronger in water, the opposite of what modern engineers expect. In the 21st century, scientists using electron microscopes analyzed Roman concrete samples, found rare minerals like strätlingite and aluminum tobermorite. These minerals form only under precise chemical and thermal conditions. They bind water and lime, creating a dense, durable crystalline network. Modern concrete made with Portland cement does not form these minerals naturally. Roman builders, through empirical experimentation, achieved a chemical process still beyond modern replication. The Pantheon dome demonstrates Roman ingenuity. Constructed 126 CE, still the largest unreinforced dome in the world. Diameter 43 meters, weighing over 4,500 tons. Built with progressively lighter concrete toward the top. Aggregate choices, heavy stone at the base, lighter volcanic pumice near the apex. No written record explains how Romans calculated the load distribution or selected materials. Yet the structure remains load-bearing after centuries of earthquakes, storms, and human activity. Even today, engineers marvel at the precision and foresight embedded in every cubic meter. Laboratories around the world attempted to recreate Roman concrete, replicating lime and volcanic ash mixtures, testing curing methods, simulating seawater interaction. Results: small-scale samples survived moderately well. Large-scale structures failed. Observations revealed ancient concrete depends on long-term chemical reactions, some taking centuries. Microclimates, humidity, and mineral impurities play a role. Replication requires more than ingredients, it requires time and environment. Engineers admit we can copy Roman concrete ingredients, but we cannot replicate its long-term durability. Roman builders sourced volcanic ash carefully. Pozzuola from the Bay of Naples region, specific chemical composition, high silica and alumina content, reacts with lime to form long-lasting crystals. This suggests Romans understood material selection at a chemical level long before chemistry existed as a science. The ash isn't just filler, it controls hydration, mineral growth, and structural integrity. Roman concrete grows stronger with age. Microcracks allow water to enter. Chemical reaction with volcanic ash produces new crystals. Crystals expand and seal cracks naturally. In essence, Roman concrete is self-healing. Modern concrete cannot do this without advanced polymer adhesives, experimental treatments, or embedded fibers. And yet, Romans achieved it intuitively, using only natural materials. Scholars and engineers remain divided. Mainstream view, Romans used empirical methods, gradually discovering what worked. Alternative view, Romans understood chemical reactions, intentionally designing self-healing concrete. Some suggest lost knowledge of large-scale material science vanished with the empire. Regardless, the fact remains, Roman concrete outperforms modern equivalents in longevity, strength, and environmental resistance. After the Roman Empire fell, trade networks collapsed. Volcanic ash sourcing became regional or forgotten. Large-scale construction halted. Empirical knowledge was never fully documented. Medieval builders returned to lime mortar, which decays much faster. For centuries, millennia-tested concrete vanished, leaving only the ruins as evidence. It was as if the Romans had created a technology centuries ahead of its time, and then history erased it. Roman harbors like Baiae, and Pozzuoli demonstrate direct exposure to seawater, lack of steel reinforcement, crystalline growth over cracks, minimal erosion or collapse after 2,000 years. Engineers today cannot build underwater concrete structures that last a few decades without continuous maintenance. Roman piers are living experiments, standing long after human knowledge failed to replicate them. Some scientists argue that time is an ingredient. Roman concrete improves gradually over decades and centuries. Curing methods, hydration, and chemical evolution contribute to durability. Ancient engineers may have intuitively relied on aging and environmental interactions. Modern methods accelerate curing artificially, bypassing the natural process that makes Roman concrete unique. Time, in a sense, is part of the recipe, something modern engineers cannot shortcut. Understanding Roman concrete fully could revolutionize construction. Sustainable, long-lasting infrastructure, self-healing marine structures, reduced carbon footprint since Portland cement production is a major CO2 contributor, bridges, roads, and buildings that survive centuries without repairs. Yet after centuries of research, the Roman formula remains elusive. Roman concrete represents more than engineering. It shows intuitive mastery of materials. It demonstrates design for longevity, not short-term gain. It reveals a society capable of complex problem-solving without modern science. Roman architects and builders may have understood physics, chemistry, and material science at a level we are only now approaching. Did Roman engineers fully understand the chemical principles or rely on trial and error? How much of the process depended on empirical observation versus intuition? Why did the knowledge vanish, and can it be recovered? Are there undiscovered Roman structures that could provide new clues? Despite modern tools and analysis, the answers remain buried in volcanic ash, lime, and millennia-old structures. Roman concrete stands as both a miracle of engineering and a historical enigma. It defies modern material science. It thrives in environments that destroy contemporary concrete. It grows stronger with time, healing itself against the elements. Centuries of experimentation, chemical analysis, and microscopy have yet to fully decode it. Roman concrete reminds us that technology is not always linear. Sometimes ingenuity appears, flourishes, and disappears, leaving the world puzzled and humbled. And in the ruins of the Pantheon, harbors, and aqueducts, that secret endures silently, waiting for someone to finally understand it.
This is the Chrono-Mist Secret. Secrets buried in time. Like the video, subscribe for the truth.